Concept E is going to focus solely on energy. So our unit is called Matter and Energy. We're kind of taking a step forward from matter and looking more into energy and how it relates to it. So by the end of this video, you should have a basic understanding of how to convert between the Celsius and Kelvin scales, and also be able to describe and distinguish the differences between heat and temperature. So we talked about conservation of matter in the last concept. Here we're talking about conservation of energy. Same idea. Matter or energy cannot be created or destroyed. Energy can only change from one form of energy to another form. All energy is accounted for as work, stored energy, or heat. So energy is simply the ability to do work. You're going to talk a lot about this next year in physics if you choose to take it. Work is the use of force to move an object a certain distance. Two types of energy. We have kinetic energy and potential energy. We're going to mention each of them. Potential energy is stored energy. It's energy that's not doing work right now, but it has the ability to if it's released. So examples of this is chemical is potential energy. This is important when we talk about chemical bonds. That's stored potential energy. But also nuclear and mechanical are potential energy forms. Examples that you might notice around you are found in coiled springs or chemical bonds that I just mentioned. Magnetism, a book sitting on a shelf that has potential energy and ability to work if it were to fall from the shelf, and so on. Now potential energy, since it's stored, it can't be directly measured, so we must convert it to kinetic energy, and it's measured using something called a calorimeter. Now, kinetic energy, on the other hand, is energy of motion. This is contained in anything that moves. Types of kinetic energy would be electrical, thermal, light energy, or all types of kinetic energy. So one thing to mention is, because kinetic energy is energy of motion, as atoms, molecules, and other particles of that scale gain kinetic energy, the particles actually move faster, and the temperature then increases. Now, temperature we're going to talk about is that measure of how fast the particles are moving. So temperature is a measure of the average amount of kinetic energy possessed by the particles of an object. So basically it's measuring how fast or slow the particles of an object are moving. So if there's low movement, that results in a low temperature. If there's high movement, that means is represented by a high temperature. So temperature is what a thermometer reads. We need to consider two scales. We have both the Celsius scale that we use in chemistry and the Kelvin scale. These are related in terms of the increments, but various points do change that we'll mention in just a moment. So Celsius, this is probably the most widely accepted use scale throughout the world. It's set up by having 100 intervals between the normal freezing point and normal boiling point of water. So it's based on the freezing point and boiling point of water between 0 and 100 degrees Celsius. Kelvin is a little bit different. This is another standard metric system of temperature, and it's commonly used among scientists throughout the world. Now, the difference between the Celsius and Kelvin scale is where that 0 degree mark is set. On a Kelvin scale, it's 273 units cooler than on the Celsius scale, and it's set with the lowest value being 0. So there's no negative values on the Kelvin scale. So this 0 point on the Kelvin scale is known as absolute zero. This is the point where the lowest temperature can be achieved possible. And representing truly the definition of temperature is that at absolute zero, the particles have stopped moving altogether, which hasn't been achieved just yet. So on the back of your reference table, you can convert between Celsius and Kelvin using the formula that you can also see on your screen. So just kind of keep that in mind. It's a very basic formula that we'll come back to at the end and see if you can apply to some practice problems. So one thing I want to mention, this part isn't in your notes, is the flow of heat. We're going to lead into this. Often when we talk about the flow of heat, there's two parts to it. There's the system, the part of the universe that the scientists, such as you, are choosing to study, and then the surroundings is everything else in the universe around it. So when we talk about the flow of heat, it's important to know what the system is and then what it's transferring or gaining energy from. So again, system would be, in this case, the liquid in the beaker, and the surroundings would be the beaker itself, the air around it, the table it's on. Some of you might have heard of the term thermochemistry. This is concerned with the flow of heat from the system to and from its surroundings, and vice versa. Alright, heat, we use this in kind of a different way in everyday life, where in chemistry it's very specific. Has a specific definition. So heat is the movement of thermal energy. Thermal energy is being transferred between a system and a surrounding as a result of a temperature difference. So again, heat is the movement or transfer of thermal energy. Thermal energy always travels from a hotter object to a cooler object. So we use the phrase in class from where it's hot to where it's not. So always hotter to colder. Alright, so here we have an ice pack. So when we look at the ankle and the ice pack, again, it's not that the ice pack is transferring coldness to the foot, because the transfer of cold is not an actual possibility. We can only transfer thermal energy from hot to cold. So here, it's the ankle that's actually transferring energy to the ice pack, and then our body registers that as it feeling cold because of the loss of energy. When heat is transferred into a system, it's reported as a positive number, and then it's referred to as being endothermic, which we talked about in the last concept. When heat is transferred out of the system, it's reported as a negative number, and then this is considered exothermic. So the loss of heat is going to be exothermic. So here's just two diagrams. On the left, you have an example of endothermic. It's going into the system, meaning it's absorbed. On the right is an example of it being exothermic, so it's moving out of the system or being released. So here are two situations. Here we have a glass of ice. What direction is the thermal energy moving? Remember, always hot to where it's not. So hand and glass of ice has to go from the hand into the glass of ice. Alright, does the system gain or lose thermal energy now that we know the direction? Well, we're going to consider the glass of ice as our system, so it's going to be gaining energy. If it's gaining or absorbing energy, then it's endothermic. Now, on the other hand, if we have a mug of hot chocolate, it's going to travel in the opposite direction, because again, hot to where it's not means it's going to go from the mug to the hand, which is where we would feel warmth as our hand absorbs energy. Now, if the system is the mug, then the system is going to be losing energy, which is considered exothermic. Okay. Now, one thing I want to point out is that although there is a direct relationship, heat and temperature are not the same. Temperature is a measure of the average kinetic energy. Heat is going to be that movement of thermal energy. So heat, measure of the transfer of kinetic energy, and this does depend on the sample size for how much kinetic energy there can be transferred. However, thermal energy is a measure of the average kinetic energy. This does not depend on sample size because of it being an average. Now, what these two things do have in common is the fact that they involve kinetic energy. Alright, so here's some practice. Pause the video, try them out. You should have set this up using the formula on the back of your reference table, plugging in 23, where the degree Celsius was, and determining that 23 degrees Celsius is equal to 294 Kelvin. Here's another one. Now we're looking for or solving for degrees Celsius. So you have Kelvin is equal to degrees Celsius plus 273. I've rearranged and inputted the 300 here, and then solve for 27 kelvins. And here's that missing part that I skipped over. So here I just simply rearranged it to solve for degrees Celsius, subtracted the values to get 27. And then finally we have sample A has a mass of 10 grams, while sample B has a mass of 1 gram. Both samples are at their freezing point. How do they compare in terms of temperature and heat energy? Well, sample A has more heat energy due to the greater amount of matter. So because there's more particles, more matter, it's going to overall have a total greater amount of kinetic or heat energy. However, because they're at the same temperature, they have the same average amount of kinetic energy. Alright, and then here we have an example where we have basically 3 different pieces that are going to be transferring energy to and from each other. We have air temperature, which is 22, steel, which is 100, and then water at 40. And we want to know how heat is going to flow. So this is where I usually set up a diagram, and I do this even for myself on a key, where I have air listed, the cylinder, and water. Then I get to see all 3 temperatures, and then I can draw arrows to show how they interact. Keep in mind that heat always travels from where it's hot to where it's not. So from the cylinder to air, but also from the cylinder to water, and then we have from water to the air. So their best chance or choice there is letter D. Okay, so again, we've talked about some temperature scales, we've talked about heat and how that compares to temperature, and then we've done some practice problems to show the flow of heat from where it's hot to where it's not.